All right, this is homework number 8. We're still practicing our integration where we have improper integrals. Determine whether the improper integral diverges or converges. Evaluate the integral if it converges, and check your results with a graphing utility. So I've got a screenshot of a graphing calculator. You could type these into Desmos as well, which is what we will be using, but I really only did it with this first one. Okay. So why is this an improper integral? Because if I put in 8, I get 1 over 0. So that's undefined. So this is the issue here. So we're going to begin by setting this up as the limit as b approaches 8 from the left, because we'd be coming at 8 from the left. Integral from 0 to b. And what do I have to do to get this thing to work? So there is a little bit of u sub happening because the inner expression does not have a derivative of 1. So u would be 8 minus x. That means du dx would be negative 1. And that means that negative du would equal dx. So in place of dx, I've got negative du. So this problem is actually, I'm just going to keep the negative here, negative 1 over the cube root of u du. And that, just for my own brain, I'm coming off of winter break here. So that's negative u to the negative 1/3. All right, so when I do this math, it's the limit as b approaches 8 from the left of, what do we have here now? So we add 1 to our exponent, so this becomes u to the 2/3. We divide by that new exponent. There's a negative out here too, so negative 3 over 2. And we're going from 0 to b. Instead of u, though, we have 8 minus x to the 2/3. All right. And then remember, you can't drop your limit notation until you actually do the fundamental theorem. So the limit as b approaches 8 from the left of, we can take out the negative 3 over 2 out here. And then I'm just plugging into 8 minus x to the 2/3. I think that might be, I don't know. I don't know if that's going to make it easier or not. Let's see. So 8 minus b to the 2/3 minus, I feel like I'm going to mess myself up with that. I already took out the minus 3/2. Okay, so minus 8 minus 0 to the 2/3. You don't have to factor the negative 3/2 out. You could leave it in there. Now I can drop my limit notation because I'm subbing in and evaluating the limit. So if I plug 8 in, I get 0 here. So negative 3/2 times 0 minus 8 to the 2/3. That's the cube root of 8, which is 2. 2 squared, which is 4. So that's negative 3 over 2 times 4, which is negative 6. Oh, wait, why do I have negative and it's positive? Oh, because this is negative. Negative 3/2 times negative 4 is positive 6. And if I check that on a graphing calculator, it gave me this. I'm curious to see what Desmos does. This is my first year switching over to Desmos, so let's just see. What is the integral from 0 to 8 of 1 over, let's see, I think it's nth root, there we go, cube root, 8 minus x. I could have also just done 8 minus x to the 1/3, right down there, dx. Yeah, now it's not giving me exactly 6 because remember, we can't actually go to 8, so it's probably getting very close. But yeah. All right, next one. So now I'm not going to, use the graphing calculator. The directions don't say that I have to do that. So, all right, so in this section, determine whether the improper integral converges or diverges. I just realized I didn't answer that. Because I got a numerical answer, this integral converges, and it converges to 6. All right, so we need to pay attention to remember whether we have p integrals or not. We're used to seeing like 1 over x to the something, and you think, oh, p integral, but that's only from a constant to infinity. So, and it's actually only like from 1 to infinity to get our formula. So, anyway, there's an improper integral because we have 0 here, and the function is not defined as 0. So, this is going to need to be the limit as a approaches 0 from the right of the integral from a to 1 of x to the negative fifth dx. I don't need to do u substitution here. I can just get right down to integrating. So that's the limit as a approaches 0 from the right of, add 1 to this, you get x to the negative fourth. So I'm going to put 1 over x to the fourth there. Divided by negative 4. I'm just going to do that then. We're going from a to 1. All right, and so then what does that come out to? I could factor the negative 1/4 out again, but that kind of made me nervous when I did that, so I'm not going to. 1 over 4 times 1 to the fourth minus negative 1 over 4 times a to the fourth. Now I can plug in my numbers. This is negative 1/4. If I put in 0 from the right, it means I'm putting in like 1 over 4 times some really tiny positive number. So you're going to get some huge positive number. So that's plus infinity. The constant is negligible. So this is infinity. That means that this integral diverges. It is a decreasing function, but it's not approaching the discontinuities at the y-axis. It's not approaching the y-axis quickly enough to make that area stop growing, basically. Okay, what if we make it 1 over the fifth root of x? It seems like x to the fifth. That tells me like the higher the exponent, the farther from the y-axis it'll be. So I bet this one will converge because now we're going from a large power to a fraction power. Otherwise, it's the same bounds. But let's just see. So this needs to be the limit as, again, 0 is the problem. A approaches 0 from the right of the integral from a to 1 of, let's write this as x to the negative 1/5 dx. So now it's the limit as a approaches 0 from the right. If I add 1 to this exponent, I get x to the 4/5 divided by 4/5 from a to 1. And that's going to be the limit as a approaches 0 from the right of 5/4 times 1 minus 5/4 times a to the 4/5. A is 0, so we get 5/4 minus 0. So this integral converges, and it converges to 5/4. So not only do we know that it has a finite area, that's what converges means, it has a finite area, but we also know what the finite area is. Okay, now this one is a p integral. It's the integral from 1 to infinity of just a nice plain 1 over x to the p. In this case, it's a p integral where p equals 5. The rule is that p needs to be greater than 1 for this to converge, so I know it converges. It didn't say to find what it converges to, but I do know that it converges to 1 over p minus 1. So it would be 1 over 5 minus 1. So it converges to 1/4. If you ever forget what that rule is, you could always do this the long way. It's not that bad. As we just did in 59 and 60, we just have a limit in a different part. All right, what about number 63? Now, u sub is not going to work here, right? Because if you let u equal x squared plus 5, there's no 2x out here to cancel out with. So my other option when I see a sum of squares, even though 5 is not a perfect square, is that this is arctangent. All right, so for this one, I guess we did do DCT, didn't we? Have we done that yet? I'm sorry, I'm coming off a break, so. Oh yeah, okay. I could have done arctangent, but I think that I would like to do direct comparison test because we're just doing whether it converges or diverges. So I don't know, maybe try that one with arctan. That might be a fun little thing to do. Okay, let's compare to, it's so close to a p integral that plus 5 is messing things up. So let's compare to the p integral expression. So, all right, so let's compare 1 over x squared plus 5 to 1 over x squared. And what is the relationship between these? So x squared plus 5 is a larger denominator. That means it's a smaller fraction overall. Like 1/10 is smaller than 1/5 or whatever. So this is less than. And I know that the integral from 1 to infinity of 1 over x squared dx is a convergent p integral. That's because the p is 2, and that's greater than 1. So what that means, remember, is that this function decreases fast enough, it approaches 0 fast enough that its area is finite. And so if this one is fast enough, then one that decreases even faster, because the graph would be sitting underneath 1 over x squared, also has to converge. So by dct, this integral, 1 over x squared plus 5 dx, also converges. We don't know what it converges to. If I wanted to figure out what it converges to, I would need to do an arctangent setup. But I do know that it converges, and that's all that I had to do. All right, number 64. This is close to a p integral again. It's not quite a p integral. I could just integrate this and see what happens. But I want to compare 1 over radical x minus 1. I want to compare that to just 1 over radical x. And I do know that this starts at 2, but remember, we're not trying to figure out what does it converge to if it converges. It's just the fact that it converges or diverges. P integrals work no matter where you start. Your answer for what they converge to could be different, but the answer to converges or diverges does not matter where it starts. Now, this number is smaller in the denominator. That means that this fraction is bigger. If we were to graph these two, you can check this in Desmos. In the long run, this graph is sitting above this graph. The reason it doesn't go from 1 to infinity, by the way, or 0 to infinity, is because that would cause 1 over square root of x minus 1 to be undefined. I know that the p integral from 2 to infinity of 1 over radical x dx is a divergent p integral because its power is 1/2. That's less than or equal to 1. That's the rule for divergence. And so by dct, if this one that's not decreasing fast enough, if this one's decreasing too slowly and continues to collect area, then the one that's going even slower, it's sitting above this graph, will also be too slow. So by dct, this integral from 2 to infinity of 1 over radical x minus 1 dx also diverges. All right, what about this one? So this one looks weird, right? Because it's like, oh, you have x times x minus 1. Now, what if, think about this. This is also known as the cube root of x squared minus x. Even though this is minus x and not minus a constant, we can still use this comparison test because that x is going to be insignificant compared to x squared when you start plugging in huge numbers. So let's compare what we have, 1 over the cube root of, I want to make it x squared minus x, just to make the comparison more obvious. Compare it to 1 over the cube root of x squared. So you always just cut off the lower term here. Because we're subtracting x, and x is positive, by the way, because it's between 2 and infinity. Because we're doing x squared minus x, this fraction will be bigger because it has a smaller denominator than this fraction. And I know that the integral from 2 to infinity of 1 over cube root of x squared dx, that's a divergent p integral. And that's because p is 2/3. The rule is that the power, if it's less than or equal to 1, you have a divergent p integral. So that means that by dct, just like the last one, if this graph is above this graph, and this graph isn't decreasing fast enough, then the one above it isn't decreasing fast enough either. So by dct, the integral of from 2 to infinity of 1 over cube root of x squared minus x dx also diverges. All right, area. These have fun little names. So find the area of the unbounded shaded region. So this one's called the Witch of Agnesi. All right, so it's the graph of 1 over x squared plus 1. Forms this nice little, looks almost like a normal distribution curve or something. It's probably not, but what's the issue here? We're going from negative infinity to infinity. And so that's where the issue is, right? There are no discontinuities here, but we have two unbounded regions. So we're trying to find the integral from negative infinity to infinity of 1 over x squared plus 1 dx. Now, looking at the graph and looking at the function, this is an even function. It does have y-axis symmetry. So instead of having to write two limit notations, I think I'm going to find the limit from 0 to infinity, and then I'm just going to double that. So I'm going to do 2 times the integral from 0 to infinity of 1 over, I'm going to write it as 1 plus x squared to make my arctan a bit more obvious. And sorry if you can hear the intercom. They're testing the intercom. And then I need to use limit notation because infinity is an improper bound. So this is going to be, let me get my limit out here actually. The limit as b approaches infinity of 2 times the integral from 0 to b of 1 over 1 plus x squared dx. This is a nice simple arctangent. We do not need u sub or anything, so I can just get right down to this answer here. So the limit as b approaches infinity of 2 times 1 over a, well, a is 1 and u is x. So 1 times arctan of u over a, or just x, goes from 0 to b. Keep your limit notation for one more round. The limit as b approaches infinity of 2 times arctangent of b minus arctangent of 0. Remember, the arctangent graph goes through 0, 0, approaches pi over 2. As you approach infinity, approaches negative pi over 2 as you approach negative infinity. So the arctangent of infinity is pi over 2. Arctangent of 0 is 0. 2 times pi over 2 is pi. In exercises 79 and 80, consider the region satisfying the inequalities. Part A, find the area of the region. Part B, find the volume of the solid generated by revolving the region about the x-axis. And part C, are we doing all three parts? Oh, I just have A and B. Huh. Part C is find the volume of the solid generated around the y-axis. I think I did do y-axis for fun. I don't know, why not? Okay, so first let's figure out this region. So we're talking about the region. It's always good to graph it, right, for each one. So 1 over x squared, y is staying above 0, x is staying greater than 1. So if I plug in 1, I get 1. And then this graph is going to go down, right? As you plug in bigger numbers for x, it's going to go down like this. It goes on forever. We're looking at this region here. So we're trying to find this area. So that would be, the area would be the integral from 1 to infinity of 1 over x squared dx. And this is great because this is just a p integral. P is 2, so this is a convergent p integral. And remember, it converges to 1, because it starts at 1 over 1 minus p. So, or no, sorry, 1 over p minus 1. It's not a negative area. So this would be 1 over 2 minus 1, which is 1. So the area is 1 for the first part. Part B says take this region and revolve it about the x-axis. It is always a good idea to draw the picture again. I know some of you are anti-drawing pictures, but it really does fix a lot of like careless mistakes we can make. If I reflect this across the x-axis, it looks something like this, and that gives me a better idea of like, is this washer, is this disk, whatever. So this is disk. There's no negative of like space here. So there's just an R. This will form like some sort of funnel type thing. R is top minus axis of revolution, so 1 over x squared minus 0. Yeah, 1 over x squared minus 0. And remember, volume, when you're rotating like this, it's pi times the integral from 1 to infinity of r squared. And that's pi times the limit as b. Oh, no, wait, I don't have to do all that. Sorry. That's pi times the integral from 1 to infinity of, that's just 1 over x to the 4th dx. So this is still a p integral that converges. And I know it converges to 1 over 4 minus 1. So this is 1/3 times pi. So pi over 3 is the volume. All right, so there's that. Let's see. Part C. I know I didn't officially do assign part C, but we might as well practice it. Now revolve around the y-axis. So still the same region here, but we're going this way. If I reflect across this axis, I have a sideways. So I have like, here's the outer portion. Remember, you connect to your axis of revolution. Here's the outer portion, and then there's this little inner portion here. So little r, big R. Big R is, well, first off, solve your equation for x instead of y. X squared equals 1 over y. X equals the positive square root of 1 over y, because these are, over here is where we're starting. These are positive x values. So r is equal to 1 over radical y minus 0, right minus left. Little lowercase r is just 1 minus 0, which is 1. And the volume using the washer method is pi times the integral from the y values, 0 to 1, of r squared minus r squared dy. So let me write out what that is. So if I square 1 over square root of y, I get 1 over y. If I square 1, I get minus 1 dy. I can integrate this, right? This is, oh wait, I should do my, sorry. I can't integrate until I do my fun little like limit stuff. So, right? Because, yeah, okay. So let's see. So pi, let's do this. The limit as a approaches 0 from the right of pi times the integral from a to 1 of 1 over y minus 1 dy. Actually, I don't need it for this. So let me separate this out. I'm not sure if this matters or not. Okay, so here I definitely need the limit notation. So limit as a approaches 0 from the right of pi times, this would be ln y from a to 1. And this would be pi times ln 1 minus ln a. Oops, I dropped my limit notation. And this is definitely 0 minus negative infinity, which is plus infinity. Because as you think about the natural log graph, as you approach 0 from the right, you're going to negative infinity. And then this part would just be pi times, this would just be like this. So minus pi minus 0, but, or plus 0, whatever. But yeah, you're getting infinity. Constant plus infinity minus constant. So this is actually divergent. I think my original answer key was wrong. I accidentally did a p integral. I guess I still got diverges, but my work was not correct. I treated this like a p integral, but that was wrong because it went from 0 to 1. So I really should have done this work for that. And then, oh, I didn't erase 81. I think I just overlooked that. Did I? Oh yeah, and then we have more stuff. I think I thought the assignment was over. Okay, let me look at these. Maybe I'll just talk through these. Sketch the graph of the hypocycloid of four cusps, x to the 2/3 plus y to the 2/3 equals 4, and find its perimeter. I guess to sketch this without Desmos, I was thinking like, if x equals 8, why did I pick that? Because I just thought of like a nice number to raise to the 2/3. If x equals 8, what could y equal? Or you could also do this, put in 0 for one of them. This is probably better. Put in 0 for one of them and see what the other variable comes out to. Either way, you get 8, 0, negative 8, 0. And then I figured, okay, the same thing would be true if I went the other way. So it makes sense that I get this thing with cusps. It tells me they're cusps, so I know about the, I know that it has to be this type of concavity to make kind of this diamond cusped shape. But you could also try experimenting by plugging in some other values. Not going to do that. Find the perimeter. Oh, I guess I did erase some of this. So that's the graph. The perimeter would be 4s, right? 4s. And s is an arc length. And remember back in chapter 7, we had an arc length formula that said it's the integral from a to b of the square root of, what was it? 1 plus dy dx squared. I think this was it. Gosh, dx. That seems right. Yeah. Okay. So in order to make this happen, I know I'm going to do this first quadrant one here. So I'm going from 0 to 8. Got that much. I need to figure out dy dx though. So let's go over here. We have x to the 2/3. Let's make it y to the 2/3 equals 4 minus x to the 2/3. And then we would need to solve for y, we would have to say, I'm going to take 4 minus x to the 2/3, and I'm going to raise that to the 3/2 power. Okay, so then find dy dx, or y prime. Power rule first, 3/2 times 4 minus x to the 2/3. Subtract 1 to the 1/2. And then chain rule. Derivative of 4 minus x to the 2/3 is negative 2/3 x to the negative 1/3. And so let's see. 3/2 times negative 2/3 is just negative 1 times 4 minus x to the 2/3 to the 1/2 over x to the 1/3. That all seems okay to me. And then remember, it's not this that we're plugging in, we're squaring that. So what is dy dx squared? Well, the negative goes away. This 1/2 power becomes 1, so it's just 4 minus x to the 2/3 on top. And then you're squaring the denominator, which is x to the 2/3 instead of 1/3 now. So now we get to come up here and say s is the integral from 0 to 8 of the square root of 1 plus 4 minus x to the 2/3 over x to the 2/3 dx. Remember, with these, instead of 1, usually you need to get a common denominator to make this happen. So we do that. Now it's the integral from 0 to 8 of the square root of, is it just 4 on top? Oh, that's weird. Okay. 4 on top over x to the 2/3. And the cool thing about this is we can square root that. Square root of 4 is 2. Square root of x to the 2/3 is x to the 1/3 dx. And we can integrate this a little bit. So the limit as a approaches 0, which is an improper integration limit there, from the right of the integral from a to 8 of 2x to the negative 1/3 dx equals the limit as a approaches 0 from the right of 2 times x to the 2/3 over 3 halves, so that's not there, from a to 8. The limit as a approaches 0 from the right of 3 times 8 to the 2/3 minus 3 times a to the 2/3. Sorry, getting a little messy here. The cube root of 8 is 2. 2 squared is 4. 3 times 4 is 12 minus 3 times 0. Now, this is equal to s. S is 12. Remember, we wanted the perimeter. So the perimeter of that entire thing is equal to 4s, which is equal to 48. Fun. Okay. Last problem. Last problem? Not the last problem. Oh, that's why I was getting confused. That says AB. Okay, anyway. Just do A and B for 99. Okay, sorry. 98. I did not erase this. Let's just talk through this one. For each integral, find a non-negative real number b that makes the integral improper. Explain your reasoning. So what would be the issue for b on part A? If I let b equal 3, then this is now an improper integral because you get 1 over 9 minus 9, which is 0. For part B, if I let b equal 4, then you get the integral of 1 over 0 when you plug it in at 4, so that's no good. For part C, I factored this a little bit, and so b could either be 3 or 4 because you have a discontinuity at either of those places. For part D, if we're integrating at ln of x, then anything between 0 to 1, I really should say b could be anything between 0 up to 1, because the natural log of x is approaching, oh no, sorry, it should just be 0. Ignore that. Because natural log as you go to 0 is undefined. It could be anything after 0, though. That's my mistake. For part E, this is tangent of 2x, so you have to think about, tangent is undefined at pi over 2. So what would b have to be to make that a discontinuity? So it's not pi over 2, it's pi over 4. Because then when you plug that in, that's where there's a discontinuity because we have a vertical asymptote. And for this one, cosine x over 1 minus sine x. So I can't let sine x equal 1 because that makes the denominator 0. So if b is pi over 2, that's what makes sine equal to 1. So for all of those, I just found where there would be a division by 0, basically, or a vertical asymptote, and that's what you're looking for. Okay, I'm going to talk through these as well. So the improper integrals, integral from 1 to infinity and integral of 1 over x and that of 1 over x squared, diverge and converge respectively. Describe the essential differences between the integrands that cause one integral to converge and the other to diverge. Remember, the integrand is just the expression here. So they're both p integrals. P equals 1 falls into the divergence rule, and p equals 2 falls into the convergence rule. There's nothing crazy happening there. Part B, sketch a graph of the function y equals sine x over the interval 1 to infinity. Use your knowledge of the definite integral to make an inference as to whether the integral converges or diverges. So you could actually do this one, right? And I'm kind of wondering about this now. So sine x, we know, will have a max and a min of 1 to negative 1. So now I'm wondering, I want to actually flip over to Desmos for a second. Going back and forth like that, I think it's kind of hard to tell what could be happening. Let me make sure I'm in radian mode. So I want to graph, what was it? It was y equals sine x over x. I'm really far zoomed out here, so. Oh, come on now. From, what was it? From 1 to infinity. So let me just change this window, sorry. Let's make this go from 1 to 1,000. I know that's not infinity, let's just let the y's go from from 0, no, from -1 to 1. Let's even make this just 1 to 100. Okay, what's happening here? I don't know, does this converge or diverge? It kind of looks like each little area might be canceling the next one out almost. So it seems like it converges or it diverges. What if we put an absolute value around this just to like make it, oh, come on. Excuse me. What I'm interested in looking at is how does this compare to something I know diverges? Is it above or below 1 over x? 1 over x sits on top of this. That makes sense because at its max, sine is 1. It makes sense that we're sitting on top of this. Now this one diverges, so that doesn't help me very much. How does it compare to 1 over x squared? So it's falling somewhere between 1 over x squared. This one converges for sure. Anything bigger than 1 over x, like 1 over x to the 1.1, this is sitting above, right? So it's kind of hard to tell. I don't know. What would your guess be? Does this converge or diverge? I was saying like, well, it seems like it decreases really quickly. Like it gets very close to 0, like pretty fast. So that seems like a finite area. If you want to actually check, you can do integration by parts. I'm not going to go through this, but you can like check and see. And yeah, it actually does come out to a convergent sum. So I thought that was kind of interesting. I think it's pretty hard to just look at a graph and say, oh yeah, that decreases fast enough. Even comparing it to 1 over x versus 1 over x squared, that's not all that helpful because it's hard to know what fast enough constitutes, I guess. All right, what was the last question here? Oh, that was the last question. Okay, this was a long assignment. Kind of ties a lot of things together. I wouldn't worry so much about those last couple. Those are just interesting sort of thinking points for you. But you definitely want to be able to recognize p integrals, do some of the limit notation, all of that other stuff.